The Pythagoras Theorem is a relationship between the lengths of the sides of a right-angled triangle. If we have two sides A and B, and then the hypotenuse of the right-angled triangle is C, this can be written as a squared plus b squared equals c squared. It's a fundamental part of many parts of mathematics, and it crops up all over the place. But how do we prove something like this? It's a relatively easy theorem to prove, and there are hundreds, if not thousands, of ways to do it. There are many books and websites devoted to cataloguing hundreds of proofs. I'll provide a link to a good website in the description below. I'm just going to give you 3 proofs, because I believe that they show 3 very unique ways of tackling the problem. The first proof I'm going to look at is a geometric proof. It's the first proof I learnt, and in some ways is the most intuitive. We start with our general right-angled triangle, with sides A, B, and C, where C is the hypotenuse. Because the area of a triangle is a half base times height, we know the area of this triangle is a half AB. Now if we take 4 of these triangles, separate them out, and arrange them like this, we see the large square has sides of length C, and in the middle of it there's a smaller square. The side length can be easily calculated here as A minus B. The area of our large square is just C squared, and the area of our small square is B minus A squared. We can also see that the area of the large square can be made from the area of the small square plus the area of the 4 triangles that make it. So this is written C squared equals B minus A squared plus 4 times a half AB. Multiplying the right-hand side out, we have b squared minus 2ab plus a squared plus 2ab. Cancelling these 2 terms, the right-hand side becomes b squared plus a squared, and so we have Pythagoras' theorem. The second proof I'm going to give is based on trigonometry. If we draw again our same right-angled triangle with sides a, b, and c, but this time include our 2 angles alpha and beta, recall from the definition of sine and cosine that the sine of alpha equals the opposite side over the hypotenuse, or b over c, and the cosine is just the adjacent side over the hypotenuse. I'm going to use the addition and subtraction formulae for sine and cosine. I'm not going to prove these identities here, but their derivation does not rely on Pythagoras, and so it's safe to use them in this proof. First we have the cosine of alpha minus beta equals cos alpha times cos beta plus sine alpha times sine beta. And secondly, sine alpha minus beta equals sine alpha times cos beta minus cos alpha times sine beta. I'm going to assume that alpha and beta lie in the range 0 to pi over 2. This is to avoid a degenerate case of triangle, such as a line or an infinite strip. First consider cos beta. Since alpha minus alpha is 0, we can write this as cos of alpha minus beta. Then by using our subtraction formula for cosine, we have cos alpha multiplied by cos alpha minus beta plus sine alpha times sine alpha minus beta. Then again by using both subtraction formulas for sine and cosine, we have cos alpha multiplied by cos alpha times cos beta plus sine alpha times sine beta plus sine alpha times sine alpha cos beta minus cos alpha sine beta. Multiplying these terms out and cancelling, we eventually end up with cos squared alpha plus sine squared alpha, all multiplied by cos beta. Because of our range for alpha and beta, cos beta does not equal 0, and therefore we can conclude that cos squared alpha plus sine squared alpha equals 1. From here we substitute in our values for cos alpha and sine alpha. Cos alpha equals a over c, and sine alpha equals b over c. And so by multiplying up by c squared, we have a squared plus b squared equals c squared. Done. The third proof I'm going to give is based on calculus. Calculus is the study of how systems change when you vary parameters. First take our right-angled triangle with sides A, B, and C. Now I'm going to increase b by a small amount, delta b. In order to keep this a right-angled triangle, c must also change by a small amount, delta c. We see the original length c lies here, and the extension delta c here. Now we have two triangles to consider, our original ABC triangle, and the new triangle we've just formed. We know one side of this triangle is delta c, and the hypotenuse will be delta b. The proof relies on the fact that these two triangles are approximately similar in the limit where delta b and delta c go to naught. Triangles are similar if they have the same basic shape, up to scaling factors. They can even be rotations and reflections of one another. If these two triangles are similar, then we know that the ratio of their sides is the same. So we can say that b over c is approximately equal to delta c over delta b. Now if we take the limit as delta b tends to naught, our fraction delta c over delta b tends to dc over db, the rate of change of c with respect to b. This is calculus notation. And so in the limit we have b over c equals dc over db, which we recognize as a separable differential equation. If we multiply up by c, we have b equals c times dc over db. Now we integrate with respect to b. And so the integral of b with respect to b equals the integral of c multiplied by dc by db with respect to b, which simplifies to the integral of c with respect to c. By using the power rule for integration, we have a half b squared plus an arbitrary constant equals a half c squared. We can first multiply by 2 to get rid of the halves here. But now we need to find what the constant of integration is. We find this by looking at initial conditions, in this case when b equals naught. If we look at our triangle with sides a, b and c, what happens in the case when b equals naught? We just have a line in this case, and so the hypotenuse collapses onto one of the sides, and we can see that a equals c. And so from the solution to our differential equation, b squared plus constant equals c squared, if we plug in b equals naught, we know that c squared equals a constant, which must equal a squared from initial conditions. And so we arrive at a squared plus b squared equals c squared. Of all the proofs, I believe this is the least rigorous. The problem lies in assuming that the triangles are similar. We should try to justify this assumption to make the proof rigorous. Going back to our two original triangles, the first one being our right-angled triangle with side lengths a, b and c, and the second has sides a, b plus delta b and c plus delta c. If I now look at the relationship between the sides by using Pythagoras' theorem, we have two equations. The first one is simply a squared plus b squared equals c squared. And the second one is a squared plus b plus delta b squared equals c plus delta c squared. By multiplying the second one out, we have a squared plus b squared plus 2 times b times delta b plus delta b squared equals c squared plus 2c times delta c plus delta c squared. If we now subtract the first from the second, we have 2b times delta b plus delta b squared equals 2c times delta c plus delta c squared. By rearranging and dividing by 2, we have b delta b minus c delta c equals delta c squared minus delta b squared all over 2. As delta b tends to naught, delta b squared and delta c squared become negligibly small compared to delta b and delta c, and so the right-hand side tends to 0 a lot quicker than the left-hand side. This leads to our approximation b over c is approximately delta c over delta b, and we can see that our assumption was valid. However, in proving this, we've used Pythagoras' theorem, so I'm not entirely convinced about this proof, although it does show there are many ways to approach this problem. These are just 3 approaches, and like I said before, there are hundreds if not thousands of different ways to do it. If you're interested, follow the link in the description, and you can have hours of fun. Maybe see if you can come up with your own proofs too. Thank you for watching, and stay subscribed for more.